Hello everybody, thank you for joining us today. My name is Minim and today we're going to be looking at permanent magnets. So, a few of our learning objectives include to define the term magnetic field, to define the term permanent magnet, and to be able to understand how to measure and plot the magnetic field around a permanent magnet. So if you're ready, let's get right into it. Okay, so I have here on the screen two examples of permanent magnets. So this one on the left here, that's kind of looks like a U. This is called a horseshoe magnet. This is because, well, it looks like a horseshoe that you would put on a horse's hooves. And over here, these ones, which are very common in schools, are called bar magnets. Okay, so the real question is, what actually is a permanent magnet? So a permanent magnet can be defined as a magnet whose magnetic field is constantly active. Okay, so some of you might ask a question now, oh, well, do we have other types of magnets whose magnetic fields aren't constantly active? Yeah, we do. Those are called electromagnets, and I'll cover those in another video. But for now, we want to look at this one word here, magnetic field. What does that actually mean? Well, magnetic field really talks about the region around a magnet that exerts, which means to really push out, a magnetic force on charged particles. Okay, so that's a very important word there, right? Charged particles. Magnets can't really affect neutral elements, right? Or neutral particles, I should say. So you know how some metals are magnetic and some aren't? Well, that's got to do with the more properties within the actual magnets themselves. So a magnetic field really talks about the region around a magnet that exerts a magnetic force on charged particles. So I have here a picture of the actual Earth. Yeah, and so the Earth has a huge magnetic field that we all constantly live in, right? So that's really got to do with the fact that the Earth has a dense spinning iron core. Now this iron core emits a magnetic field, which are shown by these field lines here, right? They're kind of faint here, but don't worry, later on in the video we're going to be looking at some field lines around bar magnets. So all you need to know for now is that the Earth has a dense spinning iron core, and that generates a massive magnetic field around the entire Earth, which is what we live in. Okay, so now you understand what a permanent magnet is and what a magnetic field is. Okay, so now let's have a look at how we actually show and measure this magnetic field around a magnet. So I have here our bar magnet. So again, let's label that bar magnet. And it's also the same at the bottom here, bar magnet. And I can see these sort of lines going around the magnet itself, right? So these lines here are called, well, field lines. And it's in its name what they represent. They really represent the magnetic field around a magnet. Over here, I have something different. These are called iron filings. So these are really that someone's taken a block of iron and they've taken a file to it and they just scraped off sort of like iron powder, right? And they sprinkled it around a bar magnet. But these two are, but this is a really visual way of seeing the magnetic field around a magnet, because to the naked eye, it's invisible, right? We can't actually see these field lines around the magnet itself. We can really only see how objects interact with the actual magnet itself. Okay, so here, there are a few key facts that you need to know about field lines, so let's write them down here. Field lines. Okay, number one, field lines always go from north to south, and that's represented by the fact that you have all these little arrows here. So you can see them all going from north. Let's trace one out. So this one is just going out into like the open, right? But really, if we were to trace this line all the way, it would actually do a massive circle, and it would join to this line here, to south. So we can see it's going from north to south. Here again, we can see if I'm going from north to south, north to south, north to south, etc., etc., etc. Okay, so that's the first thing that you need to understand, that field lines always go from north to south. Now, when we look at the iron filings, we can't actually tell which direction the iron filings are actually, well, traveling, right? But if we look very closely, we can see that the exact same field line pattern is actually traced out by the iron filings themselves. Like, let's look at this line over here, right? You can see it going from north to south. You can see these lines going out, and so on and so on and so on. Now, something that isn't really shown on diagrams but really does exist is the fact that there are field lines inside the magnet itself as well. So if I was to look at, I can't really use red because it's red. Let's do it in green. If I was to look at the north point here, there is actually field lines going from here directly there, and going here directly there. I should really do them in the middle so it's easier to see, and so on and so on. So there are field lines inside the magnet itself, right? But we don't really draw them because you can't really have something acting on a magnet inside the magnet, right? That doesn't really make sense. So we tend to leave it out, but they do exist. That's something you need to remember. Okay, now we want to understand how we can actually measure the strength of a magnetic field. Well, that's shown by the field line density. Field line density. Okay, so that sounds like a complicated word, but let's break it down. What does density actually mean? Density means to how much stuff there is in a certain volume. Okay, so really what we're looking at here is how many field lines in a certain area. Okay, so let's give a more visual example of that here. At the poles, right, so here we have a very high field line density. High field line density. Okay, I'm just going to call it FLD for now because it's too long to write out. Okay, but over here at the sides of the magnet, we don't have that many field lines per, say, square inch, right? You can see that there's quite a large distance between these two field lines. So that means there is a low field line density. So now, where there is a high field line density, high FLD, that equals strong magnetic field. And so vice versa, where there is a low field line density, that equals a weak, not low. Like, it's very easy to get trapped with saying, oh, high, low, but you want to say strong and weak. Weak magnetic field. Okay, and so how can we really see this visually? Well, if we look at our iron filings here, there are a huge amount of iron filings at the poles, right? So that shows that the iron filings are really attracted to the poles there. But there are not that many at the sides. That shows that they're not really being attracted to that area. Hence, the magnetic force of attraction there, and that's being experienced by the particles themselves. Because remember, a magnetic field is defined as the region where a electric current or charged particles, which are really the same things, or other magnetic materials are attracted. So we can see that the magnetic field strength is really weak on the sides and really strong at the poles, and that matches up to the field line density that we observed in our field line diagram up above. Okay, so now you understand field lines around the bar magnet and the three main features with field lines. So 1, they go from north to south. 2, the field line density shows how strong they are. And 3, high field line density shows strong magnetic field, and low field line density shows a weak magnetic field. Okay, hope you understand all of that. Okay, so we've just looked at the field lines around a single magnet. Now let's have a look at the field lines between two different magnets. Okay, so I have two sets here, set A and set B of magnets, right? Set A has a north magnet and a south pole, and set B has north and north. Okay, so let's have a look at how the field lines differ. Now, as always, if we remember our field line rules, the field lines always go from north to south, and that's the case here. So we can see this line is pointing away from the north pole, pointing away, so it's probably pointing something south. Here we can see that this line goes from north to south, arrows pointing that way, arrows pointing that way, etc, etc. Okay, we understand that. Now, there's something new in this field lines between two magnets, north and south. That's this region right here. So we can see that this region, the field lines are pretty much all parallel. Okay, so let's write that down. Parallel field lines. Okay, so this region actually has a very special word, and this is called a uniform magnetic field. Okay, so let's break that down a bit. Uniform. Think about in your school, you might be forced to wear a uniform, right? When you're all wearing a uniform, you all look the same, okay? So uniform magnetic field here really tells us that the magnetic strength, the magnetic field strength, sorry, of this region between North and South Pole is exactly the same across all of these field lines. So same here, same here, it's the same here, it's the same here, okay? An object placed in that portion of the magnetic field, no matter how high or low it is, right, in that little field there, it will feel the same exact force. Okay, so that's really what a magnetic field, a uniform magnetic field tells us. Okay, and let's do it in a different color. An object placed in this field at any height will experience the exact same force. Okay, so that's set A done, right? And that's quite intuitive to understand. Now let's have a look at set B, where we have like poles towards each other. Okay, again, now we have the field rules, right? North and south. The field lines always point from north to south, so we can see that they're all pointing away from north. But we have this very special region right here. Okay, where we don't get any field lines at all. So this place is actually where the repulsive magnetic force exists. Okay, so if you've ever sort of played with magnets, right, and you can see that when you put two like poles together, so north and north or south and south, and try and push them together, there is like an invisible force trying to push them apart, right? That's what really got me into physics in the first place, right? Looking at how magnets sort of behaved with each other. Okay, so having a look at those magnets pushing apart each other, that sort of force that's repulsing the magnets away from each other exists in this region right here where there are no field lines. Okay, so that's the repulsive magnetic force. Now in our hands, right, your body can pretty much overpower that repulsive force, but when you get extremely strong magnets, so when you get to superconductor level, so if you go on to do physics at A level, you learn about that, right? When you get to superconductor level, this repulsive force is so strong it cannot be overcome. Okay, that's just a little bit of extra information for you, but you just need to understand that region right in the middle where the field lines don't exist at all is where the repulsive force actually exists. Okay, so now let's have a look at how these magnetic field lines are actually plotted, right? How do we know they really exist? Okay, so now let's have a look at how we actually plot these magnetic field lines, right? So we plot them using a very special type of compass. Well, it's actually not special at all. I just call it that, called a plotting compass. Okay, so one thing that you need to understand about this compass is that the arrow, so we can see that all these plotting compasses are just like little arrows, right? The arrow always points towards magnetic south. Okay, so that's just a key feature that you need to understand about them. Right, so how do we actually plot the field lines around a magnet, right? So we take our magnet and we place it on a sheet of paper, and then we place all of our plotting magnets around the magnet at certain places, right? So these are the very common places, and you'll probably do this exact experiment in your school, right? So then, as soon as we've plotted all of our plotting compasses, right, we then underneath, so we usually do this on top of a piece of paper, underneath the plotting compass, we plot an arrow pointing whatever direction the plotting compass is pointing. And then after we've done that, we take away our plotting compasses, and then we just join the arrows, right? We join the arrows with a dashed line. And you can see that this has already been done in blue, but I'm doing it again just to sort of like give you a visual representation. Now we can see the field line around the magnet at that specific distance. Okay, so then we would repeat this on the other side, and we would also repeat this at several different distances away from the magnet to see how the field line density, remember that tells you how strong the field is, varies. Okay, so we'll put a lot of plotting compasses here, and we'll see how their arrows point, and then we'll start moving those plotting compasses away in arcs. So that's what the shape really is. It's an arc around the compass itself to get a visual representation of where its field lines are pointing and what sort of density they have.